Hello everyone, myself Monica, studying in Sri Venkateswara College of Engineering from the Department of Information Science and Engineering. My technical seminar is on blockchain-based privacy-preserving shop floor auditing architecture under the guidance of Dr. Shalini V. Ma'am, Associate Professor of Department of ISC. The contents are introduction, related background, working or implementation, future enhancement, conclusion, and references. Introduction. In the rapidly evolving of the industrial Internet of Things, securing shop floor operations, especially in audit process, is of critical importance. The unique characteristics of blockchain, such as it is unchangeable and unstructured chain, establish a solid and transparent foundation for verifying shop floor transactions and activities. We introduce a privacy-centric approach well designed to comply with strict data privacy regulations. At the heart of this transformation in the shop floor, where raw materials are converted into finished goods, here the need for efficient coordination and real-time information sharing is more pronounced than ever. Any lapse in data management or tracking can lead to significant operational disruptions, ultimately impacting the competitiveness of industrial entities. In response to these challenges, blockchain technology emerges as a viable solution, offering a decentralized, transparent, and secure method for managing and tracking information on the shop floor. We develop a unique blockchain based framework specifically designed for the IoT environment. The practical implementation strategy tailored for shop floor environments not only enhances the security of device and data integrity, but also showcases robustness against specific adversarial threats. It introduces a privacy preserving verification process that allows auditors to authenticate IoT data and device without compromising sensitive information. The related backgrounds are the combination of blockchain technology and the IoT is revolutionizing manufacturing process and advanced a synergetic effect that enhances efficiency, security, and transparency in the quickly changing industry. Blockchain based industrial Internet of Things. These approaches often do not consider the unique security challenges of decentralized systems, especially in firmware upgrade procedures, which our study aims to address. Lightweight blockchain based approaches, these methods, while efficient, do not fully address the balance between computational overhead and security robustness, while existing literature lays a strong foundation for the integration of blockchain in IoT. There remain significant gaps in practical implementation security, scalability, and real time data handling. Working or implementation. The architecture proposed in this study is designed to integrate blockchain technology within heterogeneous network environments of IoT, focusing on operational speed, transparency, legal liability, accountability, and privacy. The architecture adopts a hierarchical approach. Experimental research methodology. The experimental setup replicates a typical IoT environment with simulated local nodes, middle nodes, and full nodes interacting within a virtual network environment. This setup allows testing under various scenarios, including normal operation, high load conditions, and simulated network attacks. Architecture preliminaries. Local nodes, these are devices like sensors and actuators with limited computational capacity. They perform data collection and actuation tasks and rely on middle nodes for secure communication and data storage. Middle nodes Middle nodes act as the facilitators within the work to optimize data, produce storage. They serve as bridges within subnetworks entities and perform the majority operations. Full nodes form the backbone of the blockchain, maintaining consciousness and appending validated blocks to the chain. The FNs are chosen based on their computational capability and reliability, ensuring robustness in the blockchain network. Architecture description. The architecture facilitates a harmonious collaboration where NLS transmits data to MNS, At the core of our proposed system is a constellation of MNS that not only facilitate computation offloading but also act as a local node data custodians, significantly improving fault tolerance. Architecture workflow. Our proposed architecture has been designed considering the privacy of participants. Privacy within the network is ensured through the utilized attribute verification protocol that operates in conjunction with the blockchain in four phases: setup phase, generation phase, and validation phase. This is the figure which indicates the generation phase and the validation phase. In the generation phase, the generated data will hash of data, digest of data, and hash all the attributes where it forms the double hash formation, and it will commit to the blockchain. In the validation phase, it will retrieve the elements from the blockchain and it recreate the double hash, and it will see it will match will it match with the blockchain double hash, and it challenges the light node, and the node responds to challenges. It will verify the by middle node, and if it is yes, it will access local database and the compute to hash of raw data, and it will see if it is matching with the blockchain data hash. If it is, it will the verification will be completed. If it is no, then the verification will get failed. The working or the implementation of the proposed framework. The implementation specifies are as follows: attribute settings for the nodes were set as logical network sector, installer signature, power consumption, and transmission pattern. Hashing process. During the generation, the SHA-1 hash function has been utilized. Token issuance in registration phase. In the registration phase, each local node received 4 tokens from the middle node corresponding to the 4 attributes were later used during the validation phase. Performance matrix, key matrix such as setup phase for registration, generation, and validation phase measured to assess the efficiency of the system. Future enhancement of the project is implementing ZKPS zero knowledge proofs to allow verification of transaction without revealing sensitive information, enhancing privacy while maintaining transparency, enhancing interoperability between different blockchain platforms to facilitate seamless data exchange and auditing across supply chain networks, implementing techniques for privacy preserving data aggregation to securely collect and analyze shop floor data while protecting sensitive information, integrating secure identity management system to ensure only authorized parties have access to sensitive information during auditing, leveraging AI and machine learning algorithms for anomaly detection and predictive analytics to proactively identify potential issues or fraud in shop floor operations. The conclusions for today's topic is we proposed a privacy preserving approach to secure the shop floor auditing process utilizing the attribute verification protocol as the main building block and the blockchain technology. The proposed approach provides two main services. First, it provides a mechanism for an auditor to verify that the stored data in the blockchain has been generated by a valid IoT node in the system. Secondly, it allows an auditor to verify a set of given data has been previously generated by a specific IoT node within the system. The proposed approach exhibits several open problems as the proposed approach involves heavy computations that require relatively powerful devices. The future research direction include proposing approach that can be directly implemented on resource constrained devices. Additionally, the implementation of adapted attribute verification protocol and on IoT devices can be further analyzed. These are the references which is being referred for the technical seminar. Thank you.